Welcome to the third session of neurodynamics course. In this session, we are going to talk about separable equations. In differential equations, we have this form, right? Probably you remember all that dy over dx is equal to something. So the form of if it has a feature, then we call it separable. It means that if f of y dy equals to g of x dx, it means that here there's a function which is just a function of the variable that you have the derivative of, and you can form your equation in a way that in the right hand side of your equation there is just the other variable and its derivative. Therefore we call it separable equation, and mostly it is as the product or quotient of form that it can have. For instance, the product will be something like you have let me change the color. You have dy over dx is equal to gyfx, and for the quotient you have dy over dx equals to gy over f of x, which you know that you can also write it like f inverse of x over g inverse of y, or you can define another function, right, like h of x over I don't know, I of y. So it's just a name. So if we have this form, then we call it separable. Now we want to try that which one is actually here, which one is separable differential equations. So you can write here like dy over dx is equal to xy, which clearly is equal to f of x times g of y, which therefore this is a differential, a separable differential equation. How about the second one? The second one, you cannot write it as f of x times g of y, right? It doesn't matter how much you try. Therefore, this one is inseparable. So what should we do with this? We have, for separable differential equations, we have a method to solve it. And if it is not separable, then we have other ways that we will talk about. And how about the third one? The third one is it differential equation or not? Separable differential equation or not? You will just try, right? You can try to for instance make just the first the upper side, like you can times both of these to like something like 1 over x, to make it, for instance, to omit this part. But again it will be like y2 over x, and same in, you should actually write here like x over x, right, to make it 1. And then you will see that like 1 over x over 1 over x. It's not important, but in general you cannot again make it in a form of f of x times g of y. Therefore this is not a differential separable equation. Again, you can just you should actually try and play with this and try to make this form, but it depends on your effort, but you cannot actually. So about the third one, you can see that the fourth one, you can see that this is actually no matter how much complex it is, but this is exactly f of y times g of x. Therefore, you again call it separable. How about the how about this one? How about this one? So you can write it. So we had here we had just x minus y, right? But here we have the exponential of x minus y. This is an interesting one that you can write it like e to the power x over e to the power y, and therefore this is f of x and this is g of y. Therefore again this is separable differential equation. So we are going to actually solve one simple example here. Uh, we say we have x dot equals to x to the power 2, right? So what is the x? So we write, it's very simple, probably you are aware of, like dx over dt, you can write it x2, therefore you can write dx, you can bring x2 over here to make it in the desired form, and then bring the dt over there and take the antiderivative of both sides, and then you will be able to say that this is going to be minus 1 over x equals to t plus c. Therefore your equation will be like 1 over x equals to t plus c. Therefore you can write like x is equal to minus 1 over t plus c, right? And you can solve it for you can find the c as the constant of the integral again for particular solutions, which you can find beautiful examples in the practice sheet. But let's solve another one. So we have x dot equal to x cosine of t over 4 plus 3x to the power 3. What is the x? We're seeking for the right answer. Therefore we write like dx over dt equal to x cosine of t over 4 plus 3x to the power 3, and we are seeking for this form again, right? G of x f of y, because we want to separate these to be just depending on just one variable. Therefore we write it like dx over x, because I bring this one here and I bring this one here because there is no t in this part. Therefore I write 4 plus 3x3 equals to or cosine of t dt, right? Again, I take the antiderivative of both sides. Therefore, I have the integral of 4 over x dx plus 3 3 x2 dx, can write all of them big, equals to integral of cosine of t dt, right? So here we have this is a natural logarithm ln of x times 4 plus 3 x3, which is going, this one is going to be omitted, and here we have sine of t plus a c in general, because we have one ct here and we have one cx here, but we can say that all of them, like writing like c is equal to cx minus ct, or vice versa, like minus cx, and you can just write this part, you can write this part here, right, plus c. And yeah, that's it. And if you have some domain, for instance, if you have something like, if they tell you, for instance, take it from 0 to 1, then, or 2p, then you can find the answer over here, right? Like sine of then it's going to be like from 0 to 2p, and then this is going to be sine of 2p minus sine of 0, which is 0 in here, for instance, for this particular solution. And also in the other side, you will also have the domain in the integral, and therefore you have a very simple algorithmic algebraic equation. If you have a function like psi, which is a function of x and y, which y is itself is a function of x. So first we want to talk about it, but first let's say that this psi is just a function of x, and just solve this easy, like we want to take the derivative of it. So if we say that, okay, psi now here is equal to u over v, and psi prime will be u over v prime, which is equal to u prime v minus v u prime over v2. Therefore it's going to be sine of x derivative will be cosine of x times v minus v, which is minus v prime here, times u v prime, which is 2x sine of x over x4, right? So this is going to be x cosine of x minus 2 sine of x over x3. So if now we have, for instance, instead of this x2, if we have, for instance, y is equal to x2, then how can we find it? I mean, this was just an example to show something named chain rule. Chain rule. We want to talk about chain rule and then see whether this is correct in this example as well or not. So chain rule is that we say that psi is a function of x and y. Therefore, if we can write it like f of x times g of yx, which is not important here at all. This is going to talk about something else. I mean, d psi over dx, which just just pay attention please that this is D. This is D, right? Which has a certain meaning in mathematics. But here we have, maybe I don't pronounce it very well, but it's round of psi over round of x. It means that actually our psi is depending on some other variable of y, but we are going to just take derivative of psi in respect to x. So if you want to find the derivative of psi in respect to x, then we have this chain rule here that actually is round of psi, the derivative, the partial derivative of psi over the partial derivative of x plus round psi over the partial derivative of y times again d of y over d of x. So you can say, you can have this intuition that this is actually going to be omitted with this one, and it's just again it will just remain round psi over round x, but this is just for keep it in mind. So the first one is going to be to take the derivative in respect to x, and the second one in respect to y times this one, dy over dx. This is a very important rule. So we want to just see whether this example works like this or not. Okay, so we say that psi of x and y, let me change actually the color. So we say that psi of x and y is equal to sine of x over y. So what is the chain rule? How can chain rule actually help us to find the derivative of psi over x? So we say round of psi round over round x, like the partial derivative of our function, which is sine of x over y, plus partial derivative of psi, which is again sine of x over y, times dy over dx, right? So we say that here we can take out the y part, and therefore it's going to be this. And here we can say that we can take out the sine part, and we say round over round y of 1 over y times dy over dx, right? Therefore it's going to be y cosine of x plus sine of x times this derivative over here, right? So we say that what is actually round of I mean partial derivative of 1 over y. This is going to be 1 over this times, we also have a minus here, right? We also have a minus here. So we say if I take the derivative of this 1 minus over y squared, then it's going to be, so we also have this 2 here as well, right? Times dy over dx. I just figured out that I did a mistake here that this 2 doesn't exist. This was wrong. So this 2 doesn't exist here. And also I did this mistake that when I want to take this y over here, bringing it out, then it is going to be 1 over y and not y, right? It was a mistake. 1 over y, and so this is going to be the answer. And we said that, okay, here we have let's say that y is equal to x2, right? So y is equal to x2 in we're just going to show that whether it works or not. So we say that d psi over dx will be equal to y 1 over y, which is 1 over x2, times cosine of x plus or minus sine of x over y2, which is x4, dy over dx, because our y is equal to 2x, therefore it's going to be x squared, and this is going to be 2x, right? So so it's going to be something like cosine of x over x2 minus sine of x over x3, which is exactly times 2, which is exactly the form that we've seen over here, right? So that was just to show how this is worked, to just get familiar with this chain rule, which is a very important rule. In our work, like in the solutions which we cannot find it separable, we get some intuition out of chain rule because there is this dy over dx in it, and by this intuition we can define something named exact solution, finding the exact whether if an equation can have the form of exact equation, then we have a method to solve it. Very well. So now we are ready to talk about exact equation. With the chain rule that we talked about, we have an intuition which we will refer to, but keep it in mind that, for instance, here, if I have a function like psi of x and y, then this psi will be the first the partial derivative with respect to x, because I'm going to first take it with respect to x, and then with respect to y. This is just to show that, and here also del, I actually figured out that this is del, kind of, which the capital form is like this. So this is del 2 over del x and del y. The other form is here, right? Here you have psi yx, which is equal to first derivative, the partial derivative with respect to y first, and then, like switching the orders, and then x, right? Well, so if psi or xi is continuous, then we can actually say that this xi of x and then taking the partial derivative with respect to y will be equal to xi of yx. And definitely you know about this continuous. Continuous means that the function and its derivative should continue. For instance, take a function like y equal to I don't remember the name, but this is just going to make it positive, and then it's going to always be something like this, right? In this, in the center of the coordinate, you don't see any continuity. And also, the derivative of it should also be continuous. If, and we are mostly we are just dealing with the continuous functions. So if it happens, then we have this condition here. We also have an intuition about chain rule, which we talked about here, which I show it with 1. Therefore, with the intuition that we have from chain rule plus this thing that we got from here, why chain rule is an intuitive thing for us, because it has dy over dx right here. uh, I mean we have in our equations, maybe we have something like like a function plus another function dy over dx, which is equal to 0. Then because of this, we take the intuition from chain rule, and based on this continuity, which we have this xi of x y equal to xi of y x, then we can actually talk about some differential equations of these kinds of form, which the first term are like a function of x and y, m as a function of x and y, and n as a function of x and y, times dy over dx. Therefore, if we have a form like this, a differential equation like this, and and if we say that this m is equal to the partial derivative of xi with respect to x, and this n here is equal to the partial derivative of xi with respect to y, and also this times dy over dx. Therefore, we can say, because of this continuity condition, we can say that xi of x and then y is equal to xi of y x, which this means that actually taking the derivative of this, right, m of the derivative of y of m with respect to y is equal to the derivative of n with respect to x. Therefore, this is coming out. And if actually these two are equal, then we say that this is exact, and this is going to both sides. Therefore, this is an enough condition for having an exact differential equation. And for this exact differential equation, we have methods of solving and finding the answers. Okay, now we want to solve an exact equation. Let's say that we have, for instance, let's say that for instance we want to we face a function like this, like x2 plus 2y y prime plus 2xy plus 1 is equal to 0. We have this differential equation. We want to see whether why we should think about exact equation or not. So we say that, for instance, here we have dy over dx, and here we have x2 plus 2y times this, which is the n, plus 2xy plus 1 equal to 0. This 0 is very important part here, right? This is important. Otherwise, you should just bring all of the parts to this part. So why we think about it? Because we have dy over dx. Because of this term here, we think whether it is exact or not. So we should check. So let's check whether it is exact or not. So we say this is going to be my n or m. This is just the naming, but just for the sake of consistency, we say if it is exact, therefore it should be or it is exact if and also if and only if the m with respect to y, the differential equation of m with respect to y, is equal to the differential equation with respect of n with respect to x, right? So we should check it. Okay, this is m, and what is this? What is this? So we say okay, we can forget about that one part, and we say this is equal to just to 2x, right? And how about this part? How about this part? It's going to be over x. It's going to be 2x, right? And you can forget about the 2y part. Therefore, they are same, right? Here they are same. Therefore, it is exact equation. So, what after that? What after that? We say so we had in our condition we had psi of x with the differential equation of psi with respect to x is equal to m of y, right? This is our is equal to m. This is our point in the whole exact equation. Therefore, we say then what is psi? Then what is psi? Psi will be the antiderivative of psi x dx, which is the antiderivative of m dx, right? So we say psi will be what was the m? 2xy plus 1, 2xy plus 1 dx, which will be the we can separate it, right, like this, plus integral of 1 dx, which we can write it like dx. So it's going to be with respect to x, right? So it's going to be y x2, right, plus x plus something. So basically we were talking about in integration part we were talking about a constant like c, but here we say this term here, maybe you can have a function of actually because you took the derivative with respect to x, right? You didn't care about y, so this can be actually a function of y. Therefore, we should, for the sake of, you should, this should be complete, and so you say this is going to be plus a function of y, right? So this is, what is it? This is our psi, right? So psi is equal to this. Now, because we had the exact equation, now we say that psi of or xi of here we talked about with respect to x. Now we want to find the relationship with the n, which is here. Maybe you didn't remember. So this is going to be equal to I am going to take a derivative of y here, right? So this is going to be x2 plus 0, because here this is round of psi or del of psi with respect to y, right? Plus f prime. So we have actually we have this f prime over here, right? This means round of f over round of y, right? So what is the n? The n here, we had it. This is x2 plus 2y. Therefore, I write it in another color. This is equal to n, which is equal to x2 plus 2y. So here I can say that this is x2. This is also x2. So we forget about this part, and we say that f prime of y will be equal to 2y. Then what is f? F will be y2, right? You just take the antiderivative of it. Sorry for this keyboard which is just coming up. There's a problem here. So I am going to talk about xi now. So what is the xi? What is the xi? That we should make it complete, right? So for this xi, we said that actually we are going to say that here this xi of x, which is the m of x and y, this is showing that actually that is just the derivative with respect to those variables like x and y. Therefore, d of, based on those chain rule intuition that we have, d over dx of xi is equal to 0, right? Therefore, so it should be constant. So we have we just say that this is constant, and here we found out that xi is equal to, here we found out that xi is equal to x2y plus x plus f of y, right? What is the f of y? y2. This is equal to y2. This is equal to c, or you can say this part like minus c, and here it's going to be like plus c is equal to sorry, I just got confused. Yeah, this is our xi, the solution that based on our conditions we can find this constant like c. That what will it be? And we actually solved a differential equation which was not separable. It was not separable. Separable, sorry. It was not separable. I mean, this equation here, which we just guessed whether it is separable or not, if you try, it is not separable. And we could actually find, because of this guessing about y prime, we could find a solution based on exact equation 4. So now there is this condition that maybe it is not exact. What if it is not exact? If it is not exact, then we say that so we have a kind of form equation, differential equation form like this, right? We check, and this is not exact. Therefore, we just say that let's maybe we can find an exact form out of it. So we say that let's multiply it to something like mu just as a function of x, or multiply it to mu just as a function of y, or multiply it of mu as a function of x and y, which is harder, and we call this part as integration factor. So for integration factor, we want to talk about a form of differential equation which is not separable. It is not separable. It is not separable, and it is not exact. It is not exact, and we want to find a way to solve it. So there's a trick, right? So we want to take a differential equation. Let's take the one that we had the exam in our little exam, to check whether this is going to be separable or not. And we said that you cannot actually write it in this form. Therefore, it is not separable. So let's check whether it is exact equation or not. So we say this dy over dx plus y is equal to x, right? And then I multiply both sides to this 1 over x. Therefore, I will have 1 over x dy over dx will equal to plus y over x will be equal to 1, right? Like x over x, which is 1, right? Therefore, so I should take the one to take it to this side of the equation, right? So I can say y over x minus 1 plus okay. So this is very we have this, and this brought the idea of this form brought the idea of whether it is exact equation or not. So this is the n, this is our m. So let's check whether this is exact equation or not. So m of y is equal to, what is m of y? It's equal to 1 over x, right? And how about n of x, which is 1 over x2, right? And you see that actually they are not same. They are not same. Therefore, they are not, it is not exact equation. So with the integration factor, we are going to make it actually exact. So what should we do? So we talked about the idea, and now we are going to say that okay, I am going to multiply something like an equation, a function like mu of x times m of x y plus mu of x times n of x y, which is a function of x y, dy dx is equal to 0, right? So this is where we just this is the thing that is supposed to be exact equation, right? Because we added this mu of x to make it exact actually. So we're now going to multiply these things. Okay, I say mu of x, what is m? M is y over x minus 1 plus again mu of x, and n is 1 over x, dy over dx is equal to 0, right? So this is supposed to be exact equation, right? Therefore I am going to say that now this time I take the derivative of it with respect to y, right? Like round over round y of mu of x y over x minus 1. This will be the new, like let's I don't know, you can say that. Okay, so this mu, this doesn't depend on y, right? This is just a function of x. Now, one of the things that we use there not to use mu of as a function of x and y is for these kinds of simplicities. So we say this is going to be mu of x, the derivative of y over x. What is the derivative of y over x with respect to y? So we can forget about the 1, and therefore just 1 over x will be remained, right? Therefore here again we will talk about mu of x, 1 over x, and we want to take the derivative of it with respect to x, right? But this time actually mu depends on x, the variable that we are taking the derivative of. Therefore we say that we should say we can call like mu prime of x as its derivative with respect to x over x plus mu over x. So what is the derivative of 1 over x? It's minus x2. Therefore it's going to be this, right? dy dx, dy over dx. So so now this is equal to 0 again, right? This is equal to 0. And now we have just now we have an equation that is consisted of mu and mu prime, right? So we want to make it in clear form. Therefore we factorized mu. Therefore we say, okay, let's take a factor of mu. This is going to be 1 over x plus sorry, I did a mistake here. We took the derivative of it here, and we should say that this should be equal, right? And so there is no 0 here. So, and we say that 1 over x plus, because this minus is coming to this side, therefore it's going to be 1 over x so I also I should say that this dy over dx doesn't exist. It was a mistake. So therefore we should say that this is 1 over x plus 1 over x2. This is equal to mu prime of x over x, right? So we can also say that I am going to just say that I am going to say that I can omit delete 1 over x here, right? Okay, so what else? So I have in the clear form, I have one so I again have a differential equation here, right? So what is mu prime? Mu prime is so we have mu prime of x is equal to d mu over dx, right? So we say d mu, so we take the mu from this side to this side, and we say d mu over mu will be equal to 1 plus 1 over x dx, right? Because we also took the dx to this side as well. Therefore we say now we have again a differential equation here. What is the is it separable? Yes, of course it is, because it's like f of mu d mu is equal to g of x dx, right? Therefore I can take the antiderivative here and find the solution for mu. And what is it? It's going to be ln of mu, right? It's going to be ln of mu is equal to x plus ln of x, right? Because we have 1 and also we have 1 over x. Or let me make it clear here. 1 over x dx is going to be x plus antiderivative of 1 over x dx, which this part is ln of x. Therefore, and also we know that this e to the power, for instance, p plus q is equal to e to the power p e to the power q, right? Therefore, I can bring the exponential here. Let me write with another color, like taking putting the exponential here, and it's going to be x plus ln of x. Therefore it's going to be, this is going to be mu for just getting rid of ln, and here it's going to be ex. What is this based on this one? This is going to be e to the power ln of x, which you can actually write it as x, right? Therefore, this is going to be x e to the power x, right? So we found a function, a factor named a function named integration factor, which if we multiply this to our equation now, then it's going to be exact. So what was our equation? Our equation was this, right? This was our equation. This was our equation, which is not exact. But by multiplying this mu, now we can make it exact. And how to say that? Okay, y over x minus 1. Let's see whether actually this is true or not. So we say y over x, what was it? Minus 1 times x e to the power x. This is going to be our new m, let's say, and the other one is 1 over x e to the power x, which is our new n. Just you can call it something else, right? It's just, you can call it like p and q, or r and s, because we also have p and q over there. So let's just write it to another form, like r and s, right? So this was the thing, right? This was our equation, right? So we are going to say whether our r with respect to y, whether now it is equal to our derivative of s with respect to x. Therefore, and this s here, it's very obvious that it's going to be ex, right? Because both of them are going to be omitted, delete each other. Now we say what is r with respect to y. So we should just care about this part. Okay, let's rewrite r here. Rewrite r will be y over x times x e to the power x minus y to the minus x e to the power ex, right? Therefore r with its derivative with respect to y will be equal, so this is going to be omitted, this is going to be e to the power x, and we can forget about this part because there is no y. Therefore we say that ry will be equal, is it equal to s to the power x or not? Is it possible? So because it is y, this is e to the power x, therefore its derivative will be the same. Therefore both of them, like, it's going to be e to the power x equal to the e to the power x. Therefore we actually could create an exact equation with the help of integration factor, right? Integration factor, which was the mu that we were talking about. So now we have the exact equation, and now you can solve that equation, which I'm sure you can do this part as an exercise. So next session we will go. Now we have a lot of ideas that what differential equation is, how to solve some some classes of differential equations, like separable ones, or the ones that are like exact equations, or the ones that we can use integration factor to make it exact. And we have a lot of tools now. And I think next session we will talk more about going through dynamical systems, and then talking about the models in neuroscience, like Hodgkin-Huxley model,